Okay, let's take a look on today's daily practice. So we are going to look at the force and acceleration. So this is actually talking about the F equals ma equations, which is saying that forces can cause acceleration. So if you have force, you will have acceleration, and the motions of the object will change. If you don't have force, then of course there will be no acceleration. So this will be the major intuition of the Newton's second law, and you can also check out all these descriptions to have a better review on all these formulas and the properties. Okay, but we're going to just take a look on the problems here. So for the first one, we know that we want to relate. So we have an introductory physics student who is going to drop a textbook from a balcony into a deep layer of soft snow, which is 3 meters below, and upon hitting the snow, book sinks a further 1 meters into it before coming to a stop. The mass of the book is 5 kilograms, and assuming the constant retarding force, what is the force from the snow on the book? So in this case, we can draw a diagram to see how the problems are like. So first of all, we have a 3 meters drop from the balcony to be here, and then we also have a 1 meter snow to be over here. And then we have the textbook to first drop onto the snow, and of course there will be only gravity in this process. But then for the second step, there are actually the gravity plus the retarding force by the snow. And as you can see, because the book is going to stop eventually, the retarding force must be larger than the gravity, right? So that the book can come to a stop. Okay, so now let's take a look on the two steps. So to solve this problem here, we will also use another kinematic equations, which will be the v final squared minus the v initial squared is equal to 2as. So a will be the acceleration and s will be the total displacement. So you can derive this by using all the other kinematic equations we talk about, but this will be also one of the big 5 kinematic equations we will be using. So we use this one here because we know the displacement. So if we use the equation here, it will be a lot easier. Okay, but anyways, we can see that first of all, we will have the v final squared is equal to just 2as. So a will be the gravitational acceleration, and the distance will be just 3 meters. Okay, this will be the stage 1. And then for the stage 2 here, so notice that in this case, we will have the v final to be equal to 0, but the v initial is going to be our v final squared. And that's going to be a 2, let's call this to be a times the 1. And notice that because the v final here is going to be the same, your final velocity is also the initial velocity of the second stage. So we can actually combine them. So we combine them here to be 0 is equal to 2g multiplied by 3, and then if we just add them up, the 0 is equal to 2 times the g times a 3, and then plus a 2 times a times 1. Okay, and the acceleration here also has two components. We can think about this as, first of all, we have the downwards gravity, which will be into the downwards direction, and then we also have the retarded forces. Let's call this to be the r. So we will have this to be 6g here plus 2 multiplied by g minus r. Alright, so we can simplify this to get the twice of the r is equal to 8 multiplied by g, so r is equal to 4g. And we know that the g is going to be 10 meters per squared seconds, so we can have the r equals 40 meters per square seconds. Okay, so this will be the acceleration of the retarded force. So if we want to calculate the exact forces, we will also do so by using the F equals ma, which it will be 5 multiplied by 40 equals 200 newtons, and that's going to be the answer choice E. Okay, so that will be for the first one here. And for the second problem, we are standing on a weight scale that reads 700 newtons while holding a large physics textbook that is originally at rest. and at time t equals 1 second, you begin moving the textbook upward, so that by time t equals 2 seconds, the textbook is now half a meter higher and once again at rest. Which of the following graphs best illustrate how reading on the scale might vary with time? So for this one here, you can actually do an experiment by yourself to see how the reading of the scale is going to change. And if you just do the experiment, I'm sure that you can already pick the correct answer. But we can also draw a force analysis to show how the process will be like. So first of all, we have you standing over here, and of course, you will hold a large physics textbook. So in this case, the reading of the weight is going to be the force exerted on the weight here, which will be 7 newtons. So let's call this to be F equals 7 newtons. And then because you are trying to move the book upwards, so at first, of course, it's not going to be the entire process, but at first, since the book is moving from 0 velocity all the way onto a velocity upwards, there must be an acceleration exerted onto the textbook. So let's draw this out. So you are moving this upwards. So at the same time here, by Newton's third law, the book is also going to exert a force downwards, so to balance this acceleration. So at first, you can see that the force, total force of you on the weight is going to increase. So we will have the force is going to go up at first. But of course, when you want to maintain the speed, right, you cannot increase the speed infinitely. So there must be a stage when the force, when there will be no acceleration, the book is just going to move upwards at a constant velocity. So the force will first go up, and then you want to slow down of this a little bit, so the force is going to go down. And then eventually you will stop at some point. So this will be another stage when you want to slow down the book first, and then you are going to stop this. So there will be another case when the force is going to go downwards and then go upwards. So if we combine them all together, the answer choice E here will be correct, because this will be the case when the book is moving up. And there will be also acceleration, and then this will be the case of slowing downwards. So you can also analyze this by looking at the forces on the book.